Hello everybody. At the previous lecture we studied some simple one-dimensional cases and we applied quantum mechanics to resolve corresponding physical problems. And now we eventually arrived at a real object, and this real object is a hydrogen atom. As you can expect, when we have any quantum object, and atom is such an object, we will apply, to resolve the problem, we will apply Schrödinger equation. And Schrödinger equation need to be substituted, potential energy should be substituted in Schrödinger equation, and the potential energy of electron in atom is actually Coulomb energy, and Coulomb energy we know this U is equal to minus Z E squared over R. This corresponds to Coulomb forces, and if you substitute it in the Schrödinger equation, we will have an equation. This is Laplacian operator psi plus 2m, here is mass of electron, 2me over h squared, and here is E minus u0, minus u, and u is minus z squared over r, so plus z squared over r psi, and that is equation for stationary states, so this is equation. What is specific for this equation that distincts it from previous case, which we considered, I mean, one-dimensional potential well, for example, or oscillator, one-dimensional oscillator. The point is that this is a three-dimensional object, and we can expect, it is a safe assumption, that this object has spherical symmetry, and in this case it is reasonable to apply spherical system of coordinates. In this case we need to express this operator delta, which is Laplacian, in a spherical system. Well, the corresponding mathematics is not very difficult, but it is, I would say, there are many different transformations, and the point is, what is important is that it can be split in two different two kinds of coordinates. If it is spherical coordinates, so one part of equation will depend on radius and another will have angular dependence, two angles which are used in spherical system. But we will not resolve this equation ourselves. We will take the solution as it already known, and it is possible to prove why, in this mathematical solution, that the solution which we need, and you remember that we need a solution which obeys some requirements, and this requirements is that psi should be single valued, continuous, and finite, and such psi can be found not at any energy E, but in the case if E is greater than 0. This means that this positive energy means that it is total energy. This means that a particle is not bound by potential forces. And in this case, the spectrum is continuous. It means that E can be any. It can have any value, not necessarily, it is continuous, not necessarily some discrete values. But in case total energy E is less than 0, this means that the particle, electron in this case, is in the potential well, which is constructed by nucleus. It is a positive charge of nucleus which attract this electron, and it is bound in small value. Okay, if E is greater than 0, this means that electron is no longer belong to atom, it is free, and in this case it belongs to atom. If it belongs to atom, then it can be shown that only in the case if En is equal to minus me, e in 4th power divided by 2h squared z squared over n squared, where n is 1, 2, 3, and so forth. In this case, we can obtain psi n's, which corresponds to this ENs, and this psi n's will satisfy the requirements which are applied to psi function. If we look at this ENs, by the way, Z for hydrogen is 1, then if we look at these ENs and compare these separate values with values which were obtained in Bohr's model of atom, we will see that they are the same. So we obtain that result without any postulates, just by resolving this equation. That is a general approach. And distinct of Bohr's atom, in this case, we have the solution in a self-consistent way. This means that we don't need to take any postulates in order to explain it. And if you remember, the main problem of Bohr's atom was that it was combining a system which included both some classical physics and some, from that point of view, strange constraints which were applied by Bohr's postulates, and this solution is self-consistent. You see that in all cases we just apply the same equation, and we don't produce any additional requirements or additional properties which are not included in this equation. When we resolve this equation, we will obtain, this is En, it is Ens are eigenvalues, and the corresponding of this equation and corresponding functions are eigenfunctions. And it appears that these eigenfunctions, they contain 3 parameters. So actually psi eigenfunction is psi with three indices, n, l, and m. So this means that they depend on three parameters. The first number, n, this number, this is called principal. N is principal quantum number. Okay, all these parameters are integer numbers, and n is principal, and this n coincide with a number of energy level in a hydrogen atom, and energy depends on n. Next, L is the azimuthal quantum number. It stands for symmetry of function. We have no possibility to explain it more, but actually in books you can see, you can find some pictures with atom, hydrogen atom, which corresponds to different L. How psi and psi square, which means that probability density depends on L. You remember that for oscillator we had some different cases. If we look at the probability, it was sometimes it was like this, and if we look at higher energy, this was at this amplitude. At higher energy, it was like this, and the same it is in hydrogen atom. For L, we have a distribution which is symmetrical, like sphere. In case of L is equal to 1, we have something like such distribution if it is atom. So if for L0 it was such a distribution, for L1 it is like this, and so on and so on. This is a three-dimensional, of course, picture, and it depends, the symmetry of psi depends on L. And the third, M, is magnetic quantum number, and this magnetic quantum number, it signifies the orientation of atom. It stands for projection of momentum on some axis. And you have to understand that if we have a single atom in infinite space, there all the directions are equivalent. In order to have some axis, in order to speak about projection of momentum on some axis, we need to have this axis. And one of the methods how we can obtain such an axis, we need to have this axis physically. This should be physical axis, and physical axis we can produce with external magnetic field, for example, which will influence charged particles. So we will see later how it works. But now we have to know just that there are three quantum numbers which are parameters. So psi depends on three quantum numbers. Now n can have any value, 1, 2, 3, and so on. And L, again, all these statements they follow from accurate solution of this equation, which we did not perform, but you have just to believe me that if you manage to resolve this equation, then you will have these results. And what is the result? That is for L, so n can be any, and L can be 0, 1, 2, 3, and so on, and end to n minus 1. So totally there are n numbers, yeah? From 0 to n minus 1. And for M, we have that it can accept numbers minus L plus 1, minus L plus 2, and so on, minus 1, 0, 1, 2, and so on, and L minus 1. So, and L. So, it changes from minus L to plus L. It is easy to have some comparison with classical physics. So if L is momentum, so it is vector, and projection can have different values from plus L to minus L. Is a projection on some axis. But what is the difference between, it is just numbers. It's not a vector of projection, but it resembles what happens in classical physics. And here we see again that this is a discrete series of numbers. So if in classical physics momentum can be directed at any angle to axis, and so projection will be changed continuously. In quantum mechanics, due to this discrete numbers, it will change only by some steps. Now look, as far as we have only one number, n, which defines energy, so and function depends on three numbers. So it appears that we can have, for example, psi 1, and these numbers can be any from these combinations, any combination from these two possibilities for this number and this number. So to one n number, there is correspondence with different combinations of L and M's. So it appears that this atom, hydrogen atom, can be in different states. We remember that psi is responsible for state, or for a state of particle. So electron in atom can be different states which differs by different L and M and have the same energy. So this means that there are many different states in atom with the same energy. Such states in which have different psi's, so different psi's means different states. But if they have the same energy, such states which is the same energy but different L and M are called degenerate states. So these states are degenerate, and number of the states which have the same energy but different psi's is called a degree of degeneracy. So degree of degeneracy. Degree of degeneracy is number of states which have the same energy, so the same n, but a different size due to different L's and M's. Let's calculate how many such states exist. So what is degree of degeneracy for hydrogen atom? We will use a formula for sum of arithmetic series, and Sn, sum of arithmetic series, is n a1 plus an divided by 2. This is the first element of series, this is the last element of series, this is number of series, and this is sum of the elements. What we need to calculate? We need to calculate a sum of such a series. Look, for each n there are 2l plus 1 states. Indeed, m's is 2l plus 1 number of m's, and l's change from 0 to n minus 1. So L change from 0 to n minus 1, and for each L we have 2L plus 1 m's. So we need to calculate this sum of arithmetic series, and if we do this, if you substitute what we need to substitute, we need to substitute consequently n, here 1 plus 2n minus 2 plus 1, and divided by 2. Indeed, this is the first term, the last term, here is n, and if we cancel this and that, and we will divide by 2, we will have 2n squared divided by 2, and this is n squared. Again, this is the first term, this is the last term, and this is plus 1. So this is the first, this is the last, and this is n squared as a result. So any level in a hydrogen atom is n squared fold degenerate. Well, as I already mentioned, L is azimuthal number, quantum number, and this azimuthal quantum number, it defines angular momentum of electron in atom. We have no possibility to derive this, and we just will look at the final result. Angular momentum of electron in atom is m is defined by this number, and it is h square root of L plus 1. You see that it is quantum number, and L is quantum number, and so m can accept only discrete numbers, so it is a quantum number m. So angular momentum cannot change continuously, but by steps, by some discrete values. And projection of m on some direction, which I already explained how this direction can be organized, and this mz this is projection of angular momentum on some axis z, and it is defined by magnetic number. So it is mh, and you see that the projection is also discrete value. So this is angular momentum in atom, electron in atom, and this is a projection of this angular momentum on some axis. Now let's look at the potential well, and we will try to make a figure here. So if this is potential energy on radius of radius, it is radius which characterize distance between electron and nucleus in atom. Here is this distance, and according to this formula we see that potential energy is a hyperbola. So it looks like this. This is U on R is minus E squared on R, E squared because Z is for hydrogen is equal to 1. Well, when we substitute n equal to 1, here we can, all numbers here are known, mass, charge of electron H, that is 1, here is 1, so we can calculate this value En, and it appears that this value is minus 13.6 electron volts. And this corresponds to n equal to 1. N equal 2 is minus 3.4 electron volts, and 3 is, this is n equal to 2, n equal to 3 is minus 1.5 electron volts. This is energy, what means electron volts. If we have, for example, electron in electric field, so to obtain energy we need to multiply the charge of electron with difference of potential. So we see that when n is 1, it is ground state of electron in atom, and we need to spend energy 13.6 electron volts in order to make electron free. So to make electron free, we need to supply this energy to electron, then it will go here at this is 0 at a position where its potential energy is 0, and it will have a possibility to travel with, if E is greater than 0, so it can travel with any energy, it is free. So actually this is energy which is needed to ionize a hydrogen atom. Now, as for momentum of electron and its projection of momentum on some axis, it should be also pointed out that as we remember, in the case of momentum and coordinate, there was an uncertainty principle introduced by Heisenberg, and momentum and its projection on some axis cannot be measured simultaneously. In the case of angular momentum, there is similar rule, and this rule means that we can measure only simultaneously only m squared and projection on one of the axes. It is not possible to measure simultaneously two of projection of m. This means that if we have some axis z, and imagine that this is momentum, vector of momentum. So in quantum mechanics, this is axis z. In quantum mechanics, you can measure this projection, mz, but you cannot simultaneously have projection on this axis, and this means that you don't know where actually this m looks. So it can look at any direction here, so in this cone, because only in this, if it looks at any of these points, it will have mz projection, but we have no information about projection on this x and y. This is similar to, for angular momentum, it is similar to what we have for momentum in from Heisenberg uncertainty principle. Now let's try to build a diagram of levels of atom, hydrogen atom. It is convenient, and it is usually done in atomic physics and actually in all quantum mechanics system. So in this axis it will correspond to n, so to energy, and this direction will correspond to momentum. Electron here is n equal to 1, and it corresponds to minus 13.6 electron volts. Next level is here, and this column is for L equal to 0, and you remember that L starts from 0, 1, 2, 3, and so on. So this is in this direction L, so L equal to 0 is denoted by letter S. So S corresponds, so L equal to 0 corresponds to state S. So next is somewhere here, level 2, then somewhere 3, 4, 5, and then density is larger and larger, so I cannot enumerate all of them. So this is for S equal to 1. When we have 0, when L is equal to 1, we denote such levels with letter P. So this is P column. Again, we remember that L is less than N, and if we have P equal to P corresponds to L equal to 1, we cannot have a level here, because it should be n minus 1 maximum. So it corresponds to n equal to 2 as the lowest level with L equal to 1. The lowest level corresponds to n equal 2. So due to independence of energy of level of momentum, this is exactly at the same energy as this level at S state. So in p state it is exactly the same level. The third one is here, the fourth is here, and so on. So this column corresponds to p. Next columns is L equal to 2. It is denoted by G. So G, again, it cannot be start from 2, it starts from 3 as the lowest level in D. And again, the energy of level is exactly the same as for P and S, and for all the levels here also. Next is L equal to 3, and it is denoted by F. And this starts from 4. Maybe I need to explain why are these letters used for this moment. First, let's look what corresponds to different series. I have to remind you about spectra which are observed from hydrogen. You remember Balmer series, Lyman series, Paschen series, and so on. So Balmer series corresponds to jumps of electron, transfers of electron to the second state. You can look in corresponding lecture. So there are such transfers from this level, from this level, from that level, and so on. And also from this level, that level, and so on. And this is a Balmer series. And also Balmer series is when transfer of electron is from this level to that, So you can ask me whether it is possible also to have transfers from this level to here and from this level to this level and so on. No, it is forbidden. Why it is forbidden? There is in quantum mechanics there are so-called selection rules, and there is a selection rule for such a transfer of energy of electron in atom, which demands that in any transfers change of number L was plus minus 1. This means that you can go from this level because L is changed by 1, the same is here, the same is here, but you cannot have transfers with the same L. Why is it so? I can explain you that, okay, let's consider this, what happens when electron goes from one level to another level. It changes its energy, and where the rest of energy, when it comes here, disappear, it is taken by photon, and photon is emitted and takes energy with it. It is also specific to quantum mechanics that particles, and photon is also as a particle, has intrinsic angular momentum, and this intrinsic angular momentum is called spin of a particle, and for photon the spin is equal to 1h, and this means that if we remember that conservation of angular momentum demands that in the system, and photon is a part of the system, angular momentum conserved. So if a photon took momentum which corresponds to 1L, so momentum in residual atom should be changed also by 1L. So this is a consequence from the conservation law for angular momentum. Now this corresponds to Balmer's theory. Lyman's theory is, if you remember, with transfers to the first level, so this corresponds to Lyman's theory. So this is Lyman's theory, and this is next is this is Paschen series, and in case of absorption of radiation, it corresponds, of course, to absorption of atom in its ground state, and ground state is here, n is equal to 1. So this all transfers corresponds to emission of photons, and if a photon is absorbed by atom, so this corresponds to transfer from 1 to some other levels to p column. So absorption spectrum corresponds to transfers of type 1s to np. It is customary to denote all the states by first writing n number and then with letter denoting L number. So which states are possible? 1s, next there could be 2s and 2p here, then 3s, 3p, 3d, and so on. So now I can maybe say you about these letters, not in hydrogen atom, but in alkali metals from which these letters came. There were observed that for L equal to 1, the lines in spectroscopy, in optical spectroscopy, the series with transfers with S, the L is equal to 0, produce sharp lines. So they are not diffuse but sharp. For L equal to, they are diffuse, so we will see why later. And so it is called, D is from word diffuse. L equal to 1 is principal, is called principal. I will also explain later why it is principal. And L equal to 3 is called fundamental. So it is fundamental, diffuse, principal, and sharp. From this observation of spectroscopists, when they in the early age of quantum mechanics, they called these lines with these corresponding letters, and they are used till now.